All right, when thinking about this problem, I think it's best to break it down in terms of the different positions of the object. So, as I see it, at the top, I'm going to label this position A. That's the very beginning. Then the block's going to slide down, get to the bottom of the ramp. We'll call that position B. It's going to slide across this horizontal frictionless surface, arriving at C, and then eventually it's going to compress the spring at point D. So the next thing I'm going to do is I'm going to create a table of those 4 points, A, B, C, and D, and the different types of energy that it could possibly possess. Now at point A, the block only has gravitational potential energy, so I'm going to put an X in that box. Now as it slides from A to B, there's going to be friction, and the object is obviously going to pick up speed as it goes down, so I'm going to say that it has kinetic energy and thermal energy because of that friction. Now, once the block has picked up that thermal energy, it's going to stay throughout the rest. That block is going to keep that heat energy. So I'm going to put an X in each of these boxes at point C and D because that block will have picked it up. Now, from point B to C, it's frictionless. So it's not going to pick up any additional thermal energy during that time. So the kinetic energy at point C is going to be the same as it is at point B because of that frictionless surface. And then eventually that kinetic energy from C to D is going to be converted into potential energy in the spring, so I'm going to put an X there. Now if we look across each one of these rows, A, B, C, and D, and we look at the total energy in each one of those rows, E sub TA, E sub TB, E sub TC, and lastly E sub TD, by the law of conservation of energy, in each of those rows, the total amount of energy is going to remain constant. Now the next thing I'm going to do is I'm going to copy down onto my diagram here all of the rest of the given information. So I know that the ramp is 2.0 meters tall. The length of the incline was, the friction incline is 2.5 meters. And I also know that the spring constant here of this spring, K, would be equal to 100 newtons per meter. I also know that the force of friction on this incline is, let's see, 4.00 newtons as was given. Now it's finally time to solve. So in question A, we're asking what the total energy of the block is. If we go back to our table over to the right, the total energy at point A is going to be GPE. So GPE equals mgh. I plug in my numbers for mass of 3.0 kilograms, G 9.81 meters per second squared, and a height of 2.0 meters. Let's see here. I hammer this into the calculator. I come up with a total energy at point A of 58.86 joules. Now in part B, we're asked about the amount of energy that's converted into internal energy when it's on the ramp. Now, when energy is converted or added to a system, we typically think of that as being work. So really we're asking what work was done on the block as it slid down that ramp. Well, the work done on that block would be due to the force of friction. Now, we know W equals Fd, where F will be the force of friction of 4.0 newtons times the length of the ramp, 2.5 meters, gives us a work done of 10 joules. Now the next thing I'm going to do after I get this number down here is I'm going to go back to my table and I'm going to start to fill in some of these numbers in my table. At point A, the gravitational potential energy was 58.86 joules. In going from A to B, we know that 10 joules of that energy by way of the force of friction acting over that distance would go into thermal energy, so I'm going to put that in there. Now, once it's converted into thermal energy, it's going to stay in thermal energy. It's not going to go back into gravitational potential, kinetic, or potential energy stored in the spring. So I'm going to copy that 10 joules down all the way down to the bottom of the table. Now here I'm going to reiterate and restate my law of conservation of energy and say that the total energy at point A equals the total energy at point B equals the total energy at point C and also the total energy at point D, which is going to help me to solve for those other x's. Now I'm going to erase that one here at point B and find that the kinetic energy at point B has to be 48.86 joules because the sum of the kinetic and thermal energies has to be consistent with that 58.86 joules. Now from B to C there's no change, so I'm going to copy that 48.86 down there. And then lastly from C to D, that kinetic energy is going to get turned into elastic potential energy. Now, question C is really asking us how fast is the block going when it gets to point C? So, I know the kinetic energy, I know the mass, and I'm going to label, as I've done before, my given information, my unknowns. My unknown again was V, my mass was 3.0 kilograms, and I know the kinetic energy at point C is that 48.86 joules. So, using my equation, KE equals 1 half mv squared. I'm going to go ahead and, let's see, I'm going to rearrange that to solve for V. I find V equals square root of 2KE over m. Now I plug in my numbers and I come up with a velocity of 5.7 meters per second. Pretty easy to do. Now the last question is question D here. I want to know what the change in the length of the spring is. So my unknown here is going to be x. I know the spring constant is 100 newtons per meter. So I'm going to list that as my given information. And I know I'm going to use the equation PE sub s equals 1 half kx squared, where PE sub s is that same 48.86 joules. So I'm going to label that as my given information. And again, my x is my unknown. So rearranging to solve for x and substituting in my values, I come up with an x of 0.99 meters. I think this table strategy is pretty helpful when thinking about conversions of energy.